In this video, we are going to study about diffusion. Diffusion is the diffusion is the movement of atoms in solids. Diffusion is defined as movement of atoms in solid. Structural control in a solid to achieve the optimum properties is dependent on the rate of diffusion. Okay, so there are various phenomena which are controlled by diffusion, like carburization of steel or oxidation of a metal or decarburization. They are all controlled by diffusion rate of atoms through the surface layer. As temperature increases, diffusivity of atoms increases. Okay, so let's study the first thing, the diffusion. Let's study about the Fick's law of diffusion. So, as we know that diffusion can be defined as the mass flow process by which atoms change their position relative to their neighbor in a given phase under the influence of thermal energy and a gradient. The gradient can be a concentration gradient, an electric or magnetic field gradient, or a stress gradient. For the fixed microscopic law of diffusion, we will consider unidirectional flow of matter in binary system. We are considering binary system here, and this system is going to be consist of A and B atoms. So Fick's law states that the number of moles of B crossing per unit area, per unit time, number of moles of B crossing per unit time across a sectional plane of area A perpendicular to diffusion direction X. So this minus dA dC by dx. This d is the diffusion coefficient, A is the cross section area, and this dC by dx is the concentration gradient in x direction. So this can be written as dN by dt into 1 upon A is equals to minus d dC by dx, and this term is going to be equal to J, and J is the flux, or this can defined as flow per unit cross section area per unit time. Fick's first law can be used to describe flow under steady state condition. It is identical in form to Fourier's law for heat flow under a constant temperature gradient and Ohm's law for current flow under a constant electric field gradient. Under steady state flow, the flux is independent of time and remains the same at any cross sectional plane along the diffusion direction. We can draw the concentration distance profile for steady state, and that can be drawn as this. this. So as you can see on the screen, this is the concentration distance profile for steady state. Now let's talk about Fick's second law. Fick's second law is an extension of Fick's second law is an extension of first law of non-steady state flow. Here, at any given instant, the flux is not the same at different cross-section planes along the diffusion direction x. Also, thus, at the same cross-section, the flux is not the same at different times. Consequently, the concentration distance profile changes with time. Non-steady state flow is frequently met with practical applications of diffusion. So the expression for Fick's second law can be written as minus times of del J by del T, del X. So this is going to be del C by del T is equals to minus del by del X minus D del C by del X. So this is going to be equal to del C by del T is equals to D into del 2C by del X2, where this D may vary with concentration, and this is the Fick's second law for unidirectional flow under non-steady state condition. And this is the expression if this D if this D is does not depend on concentration. Here D is independent of concentration. Only then we can change this expression to this. And if this D depends upon concentration, then this expression will be different. Let's name this equation as equation number 1. So the solution to equation 1 for unidirectional diffusion from one medium to another across a common interface uh, is of this form. So the solution for non-steady state unidirectional diffusion is of this form. Here A and B are constants and they are determined from initial and boundary conditions of a particular problem which is given to us. And here the diffusion direction x is perpendicular to the common interface. And this expression can be written as ERF x error function of x upon 2 under root dt can be written as 2 upon root pi 0 to x by 2 under root dt e to the power minus meta square d meta, where this is the integration variable and it gets deleted as the limit of integral are substituted. So some common error functions. So error function of infinity is equals to 2 upon under root pi into under root pi by 2, which is equal to 1. Error function of minus infinity is going to be minus 1. Function of 0 is going to be 0. And ERF minus x upon 2 under root dt is going to be equal to minus ERF x upon 2 under root dt. So this was the solution for Fick's second law.